Okay, so this video is some examples of splitting field. Oh, that's purple. All right, this is about splitting fields. So this is mostly examples in C, in the complex numbers. So what are splitting fields? Okay, so for this video, I guess we'll start with we'll take Q and C. So let me just give a preliminary definition. So definition. Oh well, okay. What's a splitting field? So let F. And this is the one thing I'll do that's abstract. So let F be a field, and let F bar be an algebraic closure, right? All right. Then if f of x is in f of x, the splitting field is just the field obtained by adjoining all the roots of f of x. So the splitting field of f of x is the field, well, we'll call it split f. And this is going to be f adjoin alpha 1 through alpha d, where we've factored it. Alpha 1. Okay, so maybe we need to add a constant here. So it's some constant x minus alpha 1, x minus alpha 2, x minus alpha d for alpha 1, alpha 2, alpha d in f bar. Okay, so what we do is we take all the roots of the polynomial and we just throw them in. So and you can see that that this is split. So here we have split. You know, it breaks up, it factors, it splits. Right, all the same thing. Okay. All right, so now I'm going to give some examples of splitting fields. One second, I'm going to go grab a glass of water, I think. Okay, so splitting fields. Okay, so I got my water here. Okay, so let's do examples. I guess I'm going to call this example A. Okay, so what we're going to do is we're going to consider. So these are all going to be splitting fields of polynomials in Q. So x to the n minus 1, this is in Q of x. Okay, so this polynomial factors in C in the following way. C, it looks like it's a bunch of what are called the roots of unity. Okay, so tap tap. Okay, so here x to the n minus 1. So this is x minus z. So let's write it x minus e to the 2 pi I divided by n, and then we have to raise this to the jth power. So this to the n times j. Okay, and then we take the product of this from j is equal to 0 to n minus 1. Okay, so here this. All right, so here these guys. So these are the roots, the nth roots of unity. Okay, so these are the primitive nth roots of unity. Here we're using a formula here, so we should recall what Euler's formula says. So Euler's formula. Right, it says e to the I theta, so theta is a real number. Right, so this is cosine theta plus I sine theta. So as a complex number. And so this allows us to plot this in the complex plane. So let's plot this in the complex plane. So we're doing this in radians, and so we have this number here. So so here's the unit circle, and then this number. So this is in the complex plane. So this is 2 pi over 3, and then this angle here is 4 pi over 3. All right, and the numbers here labeled, so this, and this. So these are the third roots of unity. This is e to the 4 pi I divided by 3. This is e to the 2 pi I divided by 3. And this is e to the 0 pi I divided by 3. Or, 0 times 2 pi I guess, divided by 3. So this one number is 1. Okay, so these are the third roots of unity, and you can plot them like this. They form a group under multiplication. And this field that we obtain, the splitting field of this polynomial, is called the Nth Cyclotomic Field. Okay, so this field, the splitting field, and sometimes we call it like Kn. So this is a split of x to the n minus 1. So this is Q adjoin these numbers x to the 2 pi I j over n. And this is where j runs from, let's say, 0 to n minus 1. Okay, so here we've adjoined. So these are so we adjoin the nth roots of unity and then this field has a special name. So this is called the Nth Cyclotomic Field. Okay. This is a fan favorite amongst number theorists, and I can say a little bit more about it. So let's see. I have some. I have some notes. Maybe I'll say a little bit more about this in another video. Okay, so let's do another example, another field here. So another example. Here's like an easier example. So I called this example B. So the splitting field of x squared minus 2 in Q of x, right, is, so this is Q square root of 2 minus square root of 2, which is just Q square root of 2. Okay, so this is a simpler splitting field. Okay, so here's another one. So here's another example. Example C. Okay, so let A. Okay, so let's see. How general do I want to do this? Okay, let's just do 2. Okay, so let's do 2 or 3. Let's do 2. Okay, so let's look at the splitting field. Let's do a prime. X to the n minus p. So this is in Q adjoin X, and here P is prime. It's a rational prime number. All right, so here we have an interesting factorization, X to the n minus P. So this thing factors as, well, X minus, and then we'll do P to the 1 over n. And I'm going to view that one as a real nth root. So then we'll have zeta n X, so P to the 1 over n, and then we have X minus zeta n to the n minus 1, a to the 1 over n, where we have the following. So P to the 1 over n, so this is a real number, and this is the nth root of P, and zeta n is this 2 pi I over n. So this is what's called the primitive nth root of unity, and we call it primitive because all the other ones are a multiple of this one. It's not the only primitive nth root, but it's kind of our favorite when you're viewing it in the complex numbers. There's a way to view roots of unity not in other fields, but we'll talk about that later. Okay, so the splitting field is the following. It's L, and it's Q, and then we do a to the 1 over n, and then we do zeta n a to the 1, not a, sorry. We're going to do P. So P is a prime. So really, you can do this whole example with whatever a you want, right? And that's how I wrote it down originally. But I figure that's just kind of like extra notation. So I think this is plenty. Okay? So there's this, you adjoin all these roots. So we adjoined all these roots, and we get this splitting field, and we can do some computation to simplify this. So note that here that zeta a to the 1 over n over a to the 1 over n. So here I'm going to just use the notation zeta is zeta n. So this is equal to zeta. This is an element of L. Also, so also a to the, oh, sorry, not a. We're doing p's. I did it again. P, so also P to the 1 over n, this real number, is in L. So this tells us that that Q, P to the 1 over n, zeta n, we're just doing zetas. This zeta, this is contained in L. And conversely, that we have that L is contained in Q P to the 1 over n zeta. So this proves that L is equal to, so we have this and we have this. So we have this piece and this piece. And those two pieces tell us that we have this explicit description of the splitting field in terms of 2 generators here. So this is 2 generators rather than n generators. Okay, so a lot of the times we can simplify the presentation by doing like a little bit of algebraic simplifications. At other times, it's much more complicated to write down explicit formulas for the fields. And in fact, we will see later that you can't really, for high degree fields, you won't be able to write things down. And it is pretty much an open problem or an active area of research to find good ways of writing down these fields. This goes back to this whole idea. So this is Let me just write down another one. It's kind of harder to write down. So I wanted to say that this goes back to the idea that studying the absolute Galois group of Q is a difficult thing, but that is nebulous, and so I will talk about this later. Okay. All right. So look at this polynomial here. So this is in Q of x. Okay, and so I cooked this up so that we could graph this. Okay, so let's take the derivative here. So f prime of x. Okay, so this thing here is 3 x squared minus 3. So this is 3 times x squared minus 1. So this implies that x is equal to plus or minus 1. So those are the critical points. And so we also have, so I'm just going to do like calculus, right? So we have f of 1. So this is 1 minus 3 plus 1. F of minus 1. So this is minus 1. So this is minus 1 plus 3 plus 1. This is 2. Okay, so so this allows us to graph. So now I'm going to graph this. So like down here it goes to negative infinity. Down here it goes to positive infinity. We know that it crosses the axis here, and it'll like cross the axis here somewhere. But then we don't know what happens in between. So what happens at 0? So f of 0. So now it's going to cross somewhere between here. So f of 0 is 1 here. So let me draw this. So we have 1, 2. 1, 2. This is the value of f of 0. F of minus 1 is 2, so that's here. 1, 1. Okay, so maybe that's a little too. Okay, whatever. This is minus 1. This is 1. Okay, so it goes like this, and then at minus 1, or at 1, it's minus 1. So this is like 1 here. So here. This is 1. So it goes like this. Okay. So where are the roots of this thing? So the roots of this thing are here, here, and here. So this is alpha 1, alpha 2, and alpha 3. So they're all real numbers. So notice that alpha 1, alpha 2, and alpha 3, they're real numbers. I want to show you that this polynomial is irreducible. Okay, so note that x cubed minus 3x plus 1. So this is congruent to x cubed plus x plus 1 mod 2. Okay, so here I'm viewing this as an element of z adjoin x. And so this implies that, this implies this little fact here. So this is irreducible in the finite field here, f2 of x. That implies that this thing is irreducible in z adjoin x. And irreducibility in z adjoin x implies irreducible. This is irreducible in q adjoin x by Gauss's lemma. Okay, so we haven't really found an explicit way to write these things down, right? To write these three roots down. But we have now written down a polynomial. So the splitting field, so k is split of f. So this is a subset of the real numbers. This is irreducible here. And it does something. So we can write down this formula explicitly. We can be explicit via Cardano's formula, but it's harder. Cardano's formula, and I will send you guys a link to that, or I'll put a link down in the comments about Cardano's formula. Yeah, so we will. I will talk about that, or I'll just send a link to, because I think I saw a pretty cool YouTube video about Cardano's formula. But it gives you, it's like the quadratic formula, right? But it's a fancier version of the quadratic formula. Okay, so that gives us kind of 3 examples to talk about. Let's see, do I have another one here? No. So I just have some stuff on cyclotomic polynomials, and I'm gonna do that in another video. So these examples are some examples of splitting fields that we can compute.